Assalamualaikum warahmatullahi wabarakatuh. My name is Aiman Fikrie. My metric number is DE100143. So we are from group number 5 and we're going to present for the project which is the speed control of brushless DC motor BLDC using PID controller. So this is our group member, 5 group member. So for the introduction part, our group has decided to choose brushless DC motor as the suitable motor that we want to propose to the electrical bike company. And after we propose this brushless DC motor, we need to perform the analysis on the motor that we have decided to choose, which is we want to know what is the maximum speed capability by simulation, by doing the simulation in the lab. And then for this project also, um, our group has chosen the voltage DC voltage source, which is 60 volt. The maximum power is 1 kilowatt, and PID controller has been chosen in order to control the speed, which is why we choose PID controller, because it can maintain the value of the speed to a certain speed that we want. So which is our group, we decided to choose 400 rpm as a reference speed. And then figure on the right side here shows the construction of brushless DC motor. I think that's all for my part, and I will pass to my friends.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhamad Afiq Afandi bin Muhammad Khusrin. My metric number is DE100109. In this video, I will explain about the problem definition part. The first point in the problem definition part is a problem understanding. In the past 10 years, the development of technology system in Malaysia is evolving in a better direction. This due to the increasing use of no-fuel combustion vehicle like electric or hybrid vehicles. So this gives more advantages for this country in reducing the air pollution. Based on the APIMS website, Malaysia is the highest ranked in the rate of air pollution in the world. So to control this air pollution, every stratum of society in this country need to take part in reducing air pollution. So based on this project, the purpose of the project is to design an electric vehicle by using a simulating software. It also including PID controller to control the speed output of the motor. So the next part is objective. There are 3 objectives in this project, which is the first, to design the DC motor electric system for electric bicycle in simulating software. Next is to investigate the relationship between PID controller and the speed DC motor. And the last one is to analyze the maximum speed capability of the DC motor speed. In this project, there also has assumptions and limitation. For the first point of assumptions, the electric bicycle design will influence the speed of the motor speed. The next one is the PID controller will give a variety output speed of DC motor. The third point is the student will set the 60 volt input supply to vary the constant speed output. And the last point for the assumption is an increasement in a voltage input cause the increasement speed of the DC motor. In this project, there are only one limitation, which is the student only use the software simulation to obtain the data as opposed to using a real equipment. So by using a real equipment, the student will expose to the physical and psychomotor skill. Besides that, it also gives the very accurate data for the output of this project. The next part is an issue that related in electric drive. This figure shows that our block diagram system in this project. So there are 3 main parts in this block diagram, which is the VSI, PID controller, and the DC motor. For the VSI, it will change the unidirectional waveform to the bidirectional waveform to give a constant input voltage in this system. The technique that VSI used in this system is a full switch modulation, which is very efficient to give a constant input voltage. The next one is the PID controller. The PID controller will control the DC motor speed by give a feedback into the system. The PID controller will control the DC motor until it gives the required speed output. The last part is a DC motor. The type of DC motor used in this project is a brushless DC motor, BLDC. This type of DC motor is very high efficient and controllable to give accurate data output speed. The final part in problem definition is a related calculation in this project. There are only one calculation in this project, which is to convert from RPM speed to the kmh speed. So this is the formula for the conversion from RPM to kmh. So the equation shows that K equal to D multiplied by R multiplied by 0.001885. So the K is kilometer per hour, the D is diameter wheel, the R is RPM of the DC motor, and the 0.001885 is a constant in the formula. So when we substitute the data from the simulation, we can find out the speed of the bicycle in a kmh.
Assalamualaikum warahmatullahi wabarakatuh. My name is Akif bin Azim and my machine number is DE100184, and in this part of this video I'll be talking about the methodology of our project. So let's move on to our slide. First slide here is our block diagram. This is our block diagram of the system that we have designed in the methodology. So our input here is the reference speed, our controller here is our PID controller, our plant here is the inverter and the BLDC motor, and our output here is our output speed. We have a closed loop system, so we have a unity feedback which we connect from the output to the summing junction. So what we need to do is we input our reference speed, which is our desired speed, and this PID controller will control our inverter, and this inverter will determine which coil for the BLDC motor to energize and de-energize. And our output here will be connected back to the Hall effect sensor, and the Hall effect sensor output will be transmitted back to the trigger signal and it will be transformed into a data, and this will feed to our inverter to determine the sequence of our coil to be energized or de-energized. And our unity feedback system here is to eliminate any error from the output speed difference with the reference speed to get our final speed. So let's move on to our flowchart. Here we have our system flowchart, which first we start the system, and then the first thing we need to do is we input our reference speed. Our reference speed is 400 RPM, and then the process is PID controller tuning, which we will auto tune our PID controller, and after that we can measure our motor speed. The output motor speed, we need to make a decision whether it achieves our reference speed or not. If it doesn't achieve our reference speed, then we have to auto tune again our PID controller, and this will be a constant loop until our measured output speed is equal to our reference speed. Then only our system is a success and we can end the system. So that is all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Abdul Azim bin Muhammad Fauzi and my metric card number is DE190145. So today I will explain for the circuit and simulation for the speed control of the brushless DC motor, which is BLDC, by using the PID controller in the application of the electric bicycle. So this is the complete simulation. So I will explain in detail on what is the component and parameter that we use. First of all, this is the constant for the reference speed, which is at 400 RPM. And then this is the summing junction connected to the PID controller. This is the control voltage source, which we decide to use the 60 volt DC. And this is the universal bridge, which we use the MOSFET with the snubber resistance of 5000. And then we connect it to the BLDC, which is this is the permanent magnet synchronous machine, but we use the back EMF waveform of trapezoidal, so it matches with the BLDC, which is the brushless DC machine, brushless DC motor. And then we connect it to the bus selector to observe the output of the stator back EMF for every phase, also for the stator current for every phase, and then this is for the rotor speed and the electromagnetic torque. and then we use the output of the rotor speed to compare with the reference speed. This for the upper side here, this is for the Hall effect signal. As we can see here, the bus selector here select for the Hall effect signal for it to decode the signal and generate a pulse for it to enter the MOSFET here. This universal bridge known as the MOSFET, which have a 6 MOSFET that are used for to invert the pulse, or known as the voltage source inverter. Okay, next for the simulation part, I will explain how to do the simulation of this circuit. So what we have to do, we just have to run the simulation right here, and then before I forget, we just have to tune our PID controller right here, which is we just have to use the tuning method of transfer function based PID tuner app and tune this automatically, which is we tune the value of proportional P, integral I, and derivative D, and also the filter coefficient. This is the value that we get here, and then we use the time domain of continuous time. And then after we finalize the value of the PID and the filter coefficient, we just have to run our simulation right here, and then we will get the output which is at the scope here. We can observe the output at every scope right here. And I already run the simulation, so we will see the output in every scope, which is here. This is the output speed, which is in RPM against time. For the output speed, we can see that the graph starts with 0, and then it goes up to the top, which is around 500 RPM, and then it goes down before it reaches a steady state response. As we can see, it reaches steady state response at less than 0.1 second, and the maximum speed, as we can see here, is around 500 RPM, and then the steady state is around 400 RPM. And then when we compare it to our reference speed here, as you can see right here, this is the reference speed. The reference speed is in pink color, while the blue one is the output speed of this motor. As we can see that the steady state output of the motor is correspond to the reference speed right here, and then this shows that the PID controller helps the motor to reach the reference speed by eliminating the error. And then we observe the output torque here. This is the electromagnetic torque of the motor. As we know that in general, torque is inversely proportional with the speed, so when the speed increase, the torque will decrease. And as we can see the pattern of this electromagnetic torque, it was inversely proportional with the speed graph right here, and it also reached a steady state response in less than 0.1 second right here. And then we go to the stator back EMF waveform, and as we can see here, this is stator back EMF waveform for every phase, which is A phase is at the blue color, B phase is at red color, and C phase is in green color. And we can see that the output waveform is in trapezoidal, which behave as a BLDC, which is brushless DC motor, and the output waveform constant at less than 0.1 second, as you can see here, 0.1 second, but before that it fluctuates a little bit, and it constant at around positive and negative 30 volt. And then this is the stator current. It also the same. The first one is fluctuate a little bit, and then and in less than 0.1 second, the output waveform will reach a steady state output in less than 0.1 second, and the output of the stator back EMF and stator current match with the output speed of this motor. And this is the Hall effect signal of the motor before it goes to the decoder, and for it to generate a pulse to the MOSFET. And then this is the last one. This is the gate pulses for the motor before it goes to the MOSFET, which is the universal bridge. And in the universal bridge, it consists of 6 MOSFET, so it needs a 6 signal for it to run the motor, which is S1, S2, S3, S4, S5, and S6. This is the output of gate pulses. So that's all from me. Thank you.
Assalamualaikum. My name is Amirul bin Zuhaili, and my matrix number is DE190203. As a conclusion and recommendation, the brushless DC motor was chosen in designing this electric bicycle. The reason why we use BLDC motor is because this type of motor is one of the suitable motor to be used due to its high efficiency, and also the less losses came from this motor itself. So the less losses is because it doesn't have brush, so it will not causes the friction to happen. After that, from the result that has been discussed in the previous part, it is observed that the PID controller provides the best performance, and this we can see that when the PID controller helps to increase the time response, and then it enables the signal to reach the steady state in a very short time. After all, the electric bicycle successfully designed in the MATLAB simulator. So as a recommendation, it is recommended to increase the reference speed in order to produce a higher output speed for the electric bicycle. The one that we designed can only accelerate up to 400 rpm. In other words, it can only reaches up to 18.85 km per hour. So for the future purposes, the engineer can adjust the reference speed so that they can get their desired speed. So I think that's all from my team. Thank you.